level, I have 2 electrons or 6 electrons. The 6 electrons have 3 times more probability of being excited, as long as the transition probability per electron is the same. So, the intensity that I plot is proportional to the number of states. And that means it's also proportional to the density of states. And that's how the intensity in photoelectron spectroscopy, modulo the matrix element effect, which I'll talk in more detail, actually is telling you about the density of states and its energy. So in one shot you are getting the density of states and the energy of the material, of the electrons. Okay. There are of course some limitation. For example, we know kinetic energy cannot be less than 0. Right? Kinetic energy always has to be positive, definite. So that if we come back here, so the smallest value of kinetic energy can be 0, limiting value, which means the binding energy maximum that I can measure is equal to the photon energy. So if I'm interested in the electrons deep down, which has much larger binding energy, I have to have much larger h nu. Because h nu limits the binding energy to which I can see. So when you are interested only in the valence band, I may be happy using photon energy which is very small, but I will not see them. If I want to see them, I have to increase the photon energy. Likewise, binding energy cannot be less than 0 because then it's not bound, which tells me that the maximum kinetic energy that I'll measure, for example, for the electron that's coming out from there, is limited by the photon energy. That is necessary for me to know when I'm going to make the instrument. I have to decide how far the kinetic energy I'm going to measure. And this tells me that don't overrate your spectrometer to measure kinetic energy up to 10,000 electron volt when your photon energy is only 1,000 electron volt. Don't invest wrongly. So these are the two limits that you I am not sure that I want to talk about the other electron spectroscopies, and I'll stay with photoelectron spectroscopy because otherwise I'll run seriously short on time. But I'll tell you only about this Bremsstrahlung isochromat spectroscopy or inverse photoemission spectroscopy, because as I said, it's almost identical to the photoemission spectroscopy, because everything that I say about photoelectron spectroscopy in some way will be true for this inverse photoemission spectroscopy. What is the difference? Now I said that I can measure all the density of states, but I can measure the density of states only if electrons are there. If electrons are not there, then I can't. You say, where are the states where the electrons are not there? Well, above. So if I'm interested in knowing the states, how they're distributed above the Fermi energy, the unoccupied states, what do I do? I cannot pull an electron out from there because there is no electron. That's when we do the inverse photoemission spectroscopy. What you do is you come in with a high energy electron. That high energy electron has a probability that it will get stuck or make a transition into one of these available empty states. If it does, then this difference in energy from the high energy to this low energy that it gets stuck in, the difference in energy must be given out in some form. And a certain probability is associated with the fact that it may give out a photon. And that photon, when it comes out, you measure the photon's energy and intensity. And you can see that the energy of that photon is the difference between that energy and that energy. Since you know that energy, so you know this energy from the energy conservation. And the number of photons that are coming out is of course proportional to the number of states available there, which is the density of states. So once again, by plotting the photon intensity versus the energy of transition, you can map out the density of states of the unoccupied part. So that only for completion, I'm pointing this out, but I'll not spend time on that. It has exactly identical kind of energy conservation, and let me not spend more time on that. These are techniques that I'll not be talking about because that may not. Okay, back to photoelectron spectroscopy. There are some very important peculiarities that you must know about photoelectron spectroscopy in order to appreciate what it can do, what it cannot do, and how we can make the best use of it. One is the fact that we are measuring the kinetic energy of the electron. And remember, we are applying the energy conservation, right? Remember? Now, energy conservation I can apply only if that electron did not lose any energy when coming out. Well, if you visualize the process, you have this material that thick. Photon went in somewhere deep inside, got absorbed, electron got excited into a very high energy state. But that is not to say that the electron came out of the material. Don't confuse between the energy space and real space. It got very excited but was there deep inside. And now from the deep inside it has to travel through. There is no escape unless it travels through the material and then comes out. Once it comes out, I can say, okay, it will not interact with anything else if I have a vacuum. But while traveling through the material, it can interact with other things in the material, like with other electrons, the other atoms, other difference, that is absence of atoms. It can interact with almost anything and lose energy. If it has an inelastic interaction, that means if inelastic interaction means an interaction that takes away energy from it, then I cannot apply the conservation rule. And in fact, there is a continuous spectrum of energies that it can lose. Because of which, those electrons are lost from me and they don't contribute to the photoelectric signal. They contribute to the background, which is continuously varying. Right? So the question is, what is the probability that the electron will come out without suffering an inelastic process? Because if that probability is small, that there's a large probability of suffering the inelastic process, that means most of the electrons that I produce will not come out. And if that probability is large, that means most of the electrons that I create will come out. Now this large and small is always a comparative statement. Compared to what? Compared to how much it has to travel. So this probability that I am talking about can be cast in terms of an effective length. On an average, if I say that the electron can travel on an average something like 1 kilometer before it suffers an inelastic loss. That would mean as long as I have a 1 meter size material, all the electrons will happily come out, because on an average, some of them within 1 meter will suffer, but the probability goes as exponentially down. So it's the probability is e to the power minus d that it has to travel over lambda, but the lambda is the inelastic, this probability of suffering the interaction, and that is 1 kilometer. So e to the power minus 1 meter by 1 kilometer is e to the power minus 1 by 1000, 1000, which is negligibly small. That means almost all the electrons will come out and I'm happy. But if I say that this mean escape path is only 1 angstrom, that means anything that's starting 10 angstrom below the surface has to have e to the power minus 10 probability of coming out, which means it's almost 0. Nothing will come out. Everything will scatter, 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 scatter and come having lost all the information. So you see that the lambda, this quantity which translates into the probability of the scattering, inelastic scattering, tells me what is the information depth from the material that I can get. So approximately lambda amount of thickness I can throw. When it's getting more than lambda, so it's getting e to the power minus d over lambda. When d becomes larger than lambda, the probability is cutting it down very quickly. So e to the power minus 1 is in the order of 66%, and exponentially it's decaying if I go further. So let's think of that I can get information up to 3 lambda, approximately speaking. So it's very important to know what lambda is. And lambda is what I've plotted for you over here. As a function of kinetic energy, it happens to be a function of kinetic energy. And it happens to have this peculiar behavior. At the low kinetic energy side it's going up, at the high kinetic energy side it's going up. But if you think about it, you'll say, yes, of course it has to. Because asymptotically, we can understand how it should behave. If I have an electron, which is a kinetic energy 0, can it suffer any inelastic process? It cannot. It has no energy to give. So it will move forever, but it won't move because its kinetic energy is 0. But it will have a mean escape depth. which will go towards infinity. So as I go to lower and lower energy, because the phase space available to hand over energy is so small, the mean escape path increases. Now think of the other limit, that it's infinite kinetic energy. Infinite kinetic energy, I have a lot of energy to give, but I'll zip past so fast that there is no time to interact with the material. So in the very fast limit of electron traversing through material, it again will have very large mean escape depth. So I know asymptotically at the two ends, the mean free path is very large, going towards infinity, which means that unless it stays infinity all through, it has to have a function of this kind. And that is exactly what you're seeing. Of course, the numbers here depend on the details. And it turns out, and very significant, that at about 100 electron volt, you have as small a number as 5 angstrom, which means you are looking at a very, very thin layer of sample on the top. It's both the boon and the bane of this technique. When you are interested in the electronic structure of the bulk, you are not seeing the bulk. Because the kinetic energy, if you are here, then you are seeing 5 angstrom, lambda means about 15 angstrom approximately, as I said, 1.5 nanometers. That's all you are seeing. The surface you are looking at. And the surface electronic structure can be very different from the bulk, precisely because the periodic structure of the bulk gets violated at the surface. Surface has many difference from the bulk. So when you are interested in the bulk electronic structure, electron spectroscopy you are using, you have to be careful. In fact, this is one of the reasons why people have developed photoelectron spectroscopy to operate with very low kinetic energy and very high kinetic energy by using very low photon energy and very high photon energy. These are the more recent developments so that you can look deeper inside the bulk. I'll show you the standard techniques. Earlier used 1.5 kilo electron volt photons, but now you can do routinely experiments with 10 kilo electron volt photon, almost 10 times, so that you push so you are somewhere here, and you can push up the lambda very large and look very deep inside.
So this elastic scattering is mostly from phonons, is it?
No, it also electron-electron interactions gives to it quite a bit.
So other electrons which are also ejected, or?
Yes, and electron energy loss processes take place, not necessarily always of ionization kind, but internal excitations take place. In the low energy, you're dominated by more interaction with the lattice.
Right.
But in the high energy, and since you're most of the time in the high energy, even this 100 electron volt is huge energy for doing internal electronic excitations. And that's where electron-electron interaction, Coulombic interaction, causes a lot of inelastic processes. In fact, the technique that I did not cover, electron energy loss, is exactly that. You bring in a high energy electron and excite all these internal ones and see the structure.
So the commutation depth will also be proportional to the wavelength of the incident.
This is exactly dependence, because the kinetic energy varies linearly with the photon energy. So instead of giving kinetic energy, I can define photon energy minus the binding energy. So given a fixed binding energy, it's a photon energy axis. And that tells you with photon energy how it varies.
So then looking at the x-axis, it does seem that the losses through phonon modes are actually quite less, because the phonon energies are sub-electron volt.
Yes, but I can excite many.
Okay, so
So actually, the phonons will have some frequency, and if you convert it into energy, if your kinetic energy is much higher, then it will not interact, not get scattered by that.
That's why I said that it's the electron interaction plays a more important role. In fact, the resolution is such today that you can even see these discrete vibrational structures in your electronic spectroscopy, where you know what the losses are. Then it's not a loss process because it's again a discrete signal and you can pick it out and do spectroscopy. But I'm not going into those complications.
Question, Didi.
Yeah.
So do you have space resolution? Can you talk about local density of state, at least at a coarse grain level?
Yeah. We can, with of course, the limits and limitations. The kind of local density of states that you can talk in terms of STS, scanning tunneling spectroscopy, is really the local density of states. what you can talk about, because the photon can be bunched together, the best that you have done, and you have done quite a bit of experiments on that, is down to about 0.1 micron, 100 nanometers. So you can do space-resolved spectroscopy with a resolution of about 100 nanometers. There's another technique, which is where you don't try to bunch the photon into a very small spot. You flood the entire surface, but do exactly what you do with electron microscopy. You image that on a magnified screen, and you can push down the resolution down to 10 nanometers. There that you suffer in terms of energy, resolution, etc. And you can look at it. But all these cases, what you're talking about, that there's an inhomogeneity of electronic structure. That is no longer called a local density of states. Local density of states we refer to where there is a homogeneous, a periodic system, but the periodic system has its wave function, the particular energy that you're looking at, has its wave function differently distributed along the surface. That is, something is more concentrated on oxygen P and something is more concentrated on nickel P. So the local or partial densities of states. That is called the local density of states. The other that we are talking about, if you see even in a 10 nanometer spot, if you see an inhomogeneity, that comes from inhomogeneity of the electronic structure arising from inhomogeneity of composition or something else, but not related to local densities. And since in STS you can look at the partial densities of states, as you all know, that's why I wanted to give a competence. But where was I? Okay. I mean, where was I always reminds me of another joke that it seems that a team of explorers were lost in the mountains of Alps, and the leader, everybody is saying, so where are you going? I wanted to point out, I only talked about the pain part, the difficulties of understanding the bulk electronic structure because of this extreme surface sensitivity, but it's a boon also because if you want to know the electronic structure of the surface, no other technique can give it to you. Everything else will average over so much. Every IR that you do, it averages over a huge length scale, fraction of a micron. So that the first nanometer contribution is minuscule. You cannot figure out what's going on in the surface. They have to do a lot of very difficult things with IR to increase the surface sensitivity by doing total internal reflection, and then also they get something that they don't know what they're looking at. All electron spectroscopies, the entire family that I talked about, has this fantastic surface sensitivity. In fact, it revolutionized surface science. So electron spectroscopy once got the Nobel Prize when it was first discovered by Kai Sigman, and next time it got the Nobel Prize a few years ago, Ertl, for having discovered surface science. That time photoelectron spectroscopy was discovered and its application to surface science. It's very, very important. It has given us tremendous understanding, a probe, and to look at the surface that we couldn't have done before. And there are many phenomena today of quantum matter physics that reside only on the surface. Many, you might have heard of topological phases, etc. These are related only to the surface. And if you want to look at it, you have no other option but to come to photoelectron spectroscopy. Okay.